Classification is an important component of machine learning or predictive analytics, and we can implement classification with tree-based models. So in this tutorial, we will look at decision trees and how can we implement classification with these decision trees using this language called as R.
Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.
First, we'll just talk that what classification actually means. I'm sure a lot of you who are already a part of Great Learning would know some bit of it, but just to have all the introduction going on. Typically, the process or action of classifying something based on their shared qualities or characteristics is a process of classification. How is it different from normal profiling is that in profiling, we are explaining the classification based on similar characteristics. So basically when we are explaining the classification, it's called profiling. However, when we are trying to predict a new class or a class of some new records or new sample, that's when we call it a classification problem. And a classification can not just be a binomial classification, a two-class classification like a 0-1 sort of problem, or I tried or non-I tried, or somebody has responded to a campaign versus not responded. But it can also be a multinomial classification wherein, so for instance, if you have a total loan as a category of, let's say, a Y variable, so you can have more than two classes, let's say less than equal to 1, 2 to 5, greater than 5. So classification can be of both these two types. In general, the classification techniques that are there in analytics are, there's a trait classification technique. So trait classification can be used for either a two-class or a multi-class. CART is normally a good technique for two-class sort of binomial sort of problems. Again, random forest is also good for two-class sort of problems. Logistic regression, you can use it for both two-class, which is called the logit model, or you can use it for a multi-class, which is called a probit model. Again, neural networks is another classification technique which is good, which works good when it's used for a two-class sort of problem. So for this particular session, we will be covering some conceptual level, the details of not all these techniques. I'll not be covering neural network. I'll probably brief a bit when we are comparing the decision trees with logistic to get a flavor of that as well. And I'll also not cover random forest because these are in itself huge topics, but I'll try to see if I can in some shape and form cover it to give you a brief about them. So next is what is decision tree learning and what are different types. So you have a root node and then you have various child nodes until you reach the end of the tree, which is the terminal node, or we call the leaves. And a typical tree model where the target variable, where your dependent variable can take discrete set of values like 0, 1 or 0, 1, 2. It's called a classification tree, whereas in decision trees where your target variable can take continuous values, typically real numbers like income, income is a real or continuous value, then you call it a regression tree. Now there are many specific decision tree algorithms which are there in data science. The first is CH4.5, or you could call it C4.5. It's based on the concept of entropy and information gain. Then you have a CART model, which is classification and regression tree. It's based on the concept of Gini index and Gini gain. Then you have random forest. Random forest is an ensemble modeling, which is typically a combination of many CART trees when you and many classification trees, and you combine them, it typically is called a random forest technique. It's an extension of card technique. That's why it's also based on the concept of Gini gain. And then you have CHAID, which is chi-square automatic interaction detector. CHAID typically performs multi-level split, as I told you previously, that whenever your target variable can have a multi-level split. So for instance, let's say a loan can be less than 1, then you can have 2 to 5, then greater than 5. So whenever you have to perform multi-level split, then CHAID is a good technique for performing classification trees. CHAID is based on the concept of chi-square value. So typically it will calculate the p-value at each and every iteration and see wherever the lowest p-value is there, it will split at that particular variable. And another thing in CHAID is that normally the independent variables should be categorical in nature. If you have continuous independent variables, it's a good idea that you can bin them into finite number of bins to create categories before you actually run a CHAID technique. So these are some of the decision tree algorithms which are commonly used. So we'll move forward in terms of the classification tree learning and some of the important terms and concepts that you should be aware of. So as we discussed that whenever a decision tree works, if there will be a root node, which is usually a parent node, and you will have to split the decision trees further. So there are different splitting criteria based on the kind of algorithm you're using. So one is that you have to choose a splitting criteria. So either it could be impurity-based criteria, information gain is one of the criteria or concepts. There is Gini gain, and then there is chi-square value. So it depends on which algorithm you're using, and we'll cover it when I just proceed further. Then the next thing you have to see that whether it's a binary split, it's a 0-1 sort of split, or it's a multi-way split. Multi-way split as in it has more than 2 categories for a split. And then you have to see what is a right-sized tree. So this is typically I would say a problem or a limitation of a card technique, because a card technique usually suffers from a problem of overfitting, because there is no limitation of where you want to stop the tree and where you want to say that this is a rightly fitted tree. So when you have to find the right size tree, and this particularly applies to your card technique, then there are 2 ways that you can go about it. You can either do a pre-pruning. When I say pre-pruning, is that there is a stopping rule attached to it. So you don't allow the tree to grow too large, and then there are a lot of attributes that you can use within when you're using a card technique. There is min bucket, there is node split. You can actually tell the number of observations that you should have in your terminal node or in your leaf node, so that the tree will not grow beyond that particular point, and you can define a rightly sized fit tree. This is to avoid the problem of overfitting. We will cover a bit in brief at what overfitting means. So that is the first way of doing which is called a stopping rule of pre-pruning. The next is the post-pruning, wherein you allow the tree to grow very large and then you merge it back using pruning. So you will cut back the tree. It's based on CP, which is cost complexity parameter. Usually you can define the cost complexity parameter, and it will not go beyond that point. So these are a couple of things that you should be aware of, and these are commonly used terms when we are using a classification tree model. The idea of this webinar is not to go into too much of detail, because each of these techniques is a huge topic in themselves. So the idea is to give you the things that you should be aware of, and of course as you grow in your journey further, you can maybe explore them further. I'll try to give a flavor of each one of them. So the important terms and points to remember when you're using it. So when we're using a card technique, which is classification and regression tree technique, it uses a Gini gain concept for split. I have covered one slide in appendix which actually tells how you can calculate the Gini index and Gini gain. So I'll try to see if we have time later. I'll go through that slide. But as of now, the Gini index is usually a measure of impurity of the data partition. So it's very logically and a very commonsensical thing that you will want the data partition to be less impure. Why? Because the less is the impurity, the more data it's able to capture, the more pure it is. So you want the Gini index to be lesser, and hence the Gini gain is more. And you will see when I cover the appendix slide that because Gini index is inversely proportional to your Gini gain, so the lesser the Gini gain, the Gini index, which is a measure of impurity, the more is the Gini gain. So it will use Gini gain as for the splitting criteria. So whichever node and whichever variable at whichever split point it gives the maximum Gini gain, there it will split the particular node. Then we talked about that the cart model usually suffers from the problem of overfitting, right? Now, what overfitting means is that as the number of nodes increases or whenever your tree size goes longer, then what happens is that the accuracy in your development sample, and I'm sure most of you will be aware of development sample and test sample. So development sample is the one where you actually train your model, and the test sample is one where you will test your sample to see how good the model holds on an unseen sample. So that's the difference between development sample and test sample. So what happens is that in the cart model, whenever you allow the nodes to increase further and further and the tree size goes longer, the accuracy in the development sample increases, but after some point of time, the accuracy in your test sample, where it should actually hold true, tends to start decreasing, and you know that your model is suffering from the problem of overfitting. So that's something that you have to be careful about. And that's why random forest is a better technique than cart, because of so many trees at time, it averages out the problem of overfitting, and it doesn't suffer that much from a problem of overfitting, whereas a cart model does. But there are ways to fix that as well, as we discussed previously. You can prune the tree, you can do a stopping rule, but in general, the cart model suffers from this problem. Then there is a term which is called entropy. So entropy is a measure of randomness in the data, and you usually want the data to be less random so that the split can capture more and more data, and hence at each split there is less data which is lost. So entropy, whenever entropy is 0, which means that your sample is completely homogeneous, there is no partition at all. And whenever entropy is 1, which means it's equally divided into 2 categories. Then entropy gain or information gain is a concept which we use in the classification technique CH4.5. So CART is based on Gini gain. Entropy or information gain is used in CH4.5. Entropy and information gain are also so information gain is usually 1 minus your entropy. So lower the randomness or entropy, more is the information gain, and that attribute is used for splitting the tree in CH4.5. So we have covered CART, we have covered CH4.5, the conceptual level things and what it is based upon. And then the shade, as I previously told, it uses the chi-square concept for split. So basically the lowest p-value it will use to split the tree. And now I think one of the important things that you should be aware of is that how each of these techniques differ from each other. So for instance, if we say shade and CART, how are they different? Even though they are used for decision tree model, even though they are used for classification tree model, how can you tell that when to use a CART, for instance, and when to use a shade? So there are some fundamental differences between these techniques. So one of the difference, for instance, is that the CART model, as I told previously, is usually good for a binary split, wherein, for instance, you just have to split the node in 2 parts. Let's say yes or no, less than equal to 25 or greater than 25. But your shade model works very well when you have a multi-way split. And we will see in the example of the gold loan attrition problem where we used shade that how it can split a particular node into more than two categories as well. And another thing is that typically in trade, as I told you previously, that it's a good thing that your independent variables are categorical in nature. If they are continuous, you'll have to bin them and you have to use them as categorical variables. Whereas in cart model, it's okay if even if you have some continuous variables, it will still work fine. But and then there are methods how the cart model will treat the real or the continuous variables. There are methods attached to that as well. But in general, it can handle that. And then trade does not suffer from the overfitting problem, whereas the cart model usually suffers from an overfitting problem. So then we will now see that why it's a good technique, what are some of the advantages of using a tree model, and we will see how is it different from a logistic regression technique, because it's a very important concept that we will be covering when we cover the difference between tree model and logistic regression model. So first of all, why is it a good technique, a tree model technique? So first is that it's a good technique for feature selection. So typically, even if you're not using a decision tree, let's say for creating the actual model, it's in a way a good technique for identifying important variables for feature selection. So typically in segmentation, if you have to see which segments are important ones, apart from the normal unsupervised segmentation technique, decision tree is also considered as one of the segmentation techniques because it gives you the segments, and we will see how it will give you the segments. And then one of the other advantages it has is that it's easy to interpret. As we all know, it's very intuitive output. If your business is somebody who doesn't understand machine learning, etc., they want very easy to interpret output, and decision tree is the go-to model. It also requires very less cleaning as compared to regression techniques, because we know that regression techniques usually suffers from, there are a lot of conditions and assumptions that you have to fulfill before using a linear or a logistic regression. It suffers from multi-collinearity problem. You have to see that there are no correlated variables attached to it. It gets impacted a lot by the outliers and missing values. So there is a lot of manual work which is there in the logistic regression model, whereas in the tree-based model, it comparatively requires less amount of cleaning than when you compare it with regression techniques. And also another key difference is that your tree-based model is able to capture non-linearity in the data as well, better than the regression models. Because in general, in real, not every time you will have linear relationships, and there will be a lot of non-linearities in data. The independent and the dependent variables are not linearly related to each other. So that's where the tree model is able to capture the non-linearities better in the data. So now we will see the difference between the tree model and the logistic regression model. Now, this is a very important concept which is called the bias variance trade-off. What this means is that in general, you will want your model, it's an ideal scenario, you will want the model to be low in bias and low in variance. But it's very difficult to have low bias and low variance at the same time, because if you will have low bias, there is a tendency that there will be a higher variance and vice versa. So your decision tree model are usually considered as low bias algorithm. And why is it so? What actually bias means is, bias means that how much on an average are the predicted values different from the actual values. Okay, so because there will be some predicted values, there will be an actual value, and the difference is called the bias error. So you want the bias to be low because you don't want the predicted values and actual values to differ too much. And that's where decision trees are low bias algorithms, and it falls back to the same thing which I told you previously, because it's able to capture non-linearities in data better, and hence it's a low bias algorithm. Whereas your logistic regression model, it's not able to capture the non-linearities in data much, and hence it's a high bias algorithm. Whereas your decision trees, while it's a low bias, it's a high variance algorithm. What we mean by high variance is that, so what variance means is that how much variation will you see in your prediction when you're using a different training sample. So for instance, what may happen is that, so for example, let's take an example of when we are trying to predict a credit score of a particular person. In terms of probability, if we see, if you're using one of the training samples, let's say it's 0.9. If you use another training sample, it's 0.7. If you use another training sample, it's 0.8. So this is not right, because your probability of credit score is fluctuating when you use a different training sample, which means that your algorithm is suffering from high variance problem, and we want the variance to be low. So even if you change the training sample, even if you change your sample, the predicted values don't vary a lot. But your decision trees is usually a high variance, and that's why it suffers from the problem of overfitting. And if you change the sample, then your output tends to vary a bit. So there are ways to take care of high variance and low bias, ways to treat them. This is the nature of the tree model, whereas your logistic regression model, even if you change the training sample, the output will not vary too much. And hence, it's usually used a lot in financial services organizations, because when you're trying to predict at a very granular level, it's a good idea to use a logistic regression model. So another key difference between a tree model and a logistic regression is that if you've used a tree model, you will see that it gives you it gives you a score, but it gives you that predict or a score of that at a particular split. So for instance, if you're using a card technique, and if you split at an age variable, it will tell you that age is less than 25, let's say, or greater than 25. Or if it combines, let's say, age between 10 to 25, then it will give you that score at a combined age level from 10 to 25. It will not give you at a very granular level that, let's say, if you change the age from 20 to 21, what will be the impact? And that's where a logistic regression model is better, because it gives you more granular level information. The predict score, which it gives you, it tells you that for each incremental change in that variable, let's say for age, if you incrementally change the age from 20 to 21, from 21 to 22, for each incremental change, how your probability changes, how your dependent variable changes, which is usually your log odds. So that's why it's always a good idea to use whenever you're predicting, let's say, a fraud or a credit score. It's a very good idea to use a logistic regression, and that's why a lot of financial services firms have affinity towards logistic regression. Even though for marketing problems, you can still use a segmentation, you can still use a tree-based model or machine learning model, because they are more black box. So the only thing which matters is how good your model is, how accurate your model is. So as far as your accuracy is good, even if you wrongly predict few of the customers in a marketing problem here and there, it doesn't make that much of a difference. Whereas in a risk-based problem, in a fraud-based problem, where each customer has a huge value attached to it, you will not want to even wrongly predict a single one of them, and hence it's a good idea to use a logistic regression at that point of time. So that's a bit about the difference between these two techniques. So now we will be covering the goal loan attrition problem. So I'll give you the context of this business problem. So the business context of this problem is that this is a gold loan business which was started by the rural business of one of the clients that I worked with. And they were having the current account receivables. I'll explain, there are some technical terms in it. I'll tell what each of these terms means. So they were having current account receivables of, let's say, XX crores at the end of March 17. And they were seeing that every month, about 60% of the disbursement amount, which is in terms of customers, I tried, which means that they come and they take a gold loan. So what a gold loan will usually do is that you will give, let's say, 1 lakh worth of gold you're giving, and you will get in return, let's say 75,000 of loan. So you're giving gold as a mortgage, and you're getting back the loan. So you're giving as a collateral basically. And what it says is that usually people come and take this whole loan, but I tried very soon, and hence the customer was losing on the interest amount, because whenever you're giving a loan, how will be you generating money as a customer, as a client? You will be getting the interest amount on that every month, and hence if people are not fulfilling their entire tenure period, which means you will be losing out on your interest amount, which will directly impact your account receivables. So account receivables is nothing but the amount of money that you will be generating through each of these customers. So hence, you will be losing out on your interest amount, and hence it will be impacting your account receivables. So it was very important to understand that who these customers are through the data. Are there any specific segments of customers that we can target? What are their requirements? What are their behavioral attributes? What's their texture? And how hence we can control this attrition. And for implementation, they wanted us to design some targeted campaigns for the required segments of these customers. So it's not a usual segmentation problem, because it's a supervised model, because we know and we had calculated the target variable. So that's why I told you previously as well that even when you're trying to understand the segments, and it's a supervised technique, you can use classification-based techniques. So, so what are some of the steps that we have taken to work on this problem? So it's a normal attrition-based problem, where we have to understand that why this attrition is happening, how we can control, what are some of the customers who are attriting more than other, and how we can design some of the campaigns to control that. So the first thing that we usually do is that and this is very real in nature, because these are the actual steps that we have taken. So you can probably draw parallels to some of the work that you have done, or some of the work that you want to do in your capstones or in your existing projects. So I've tried to give it a real flavor, because a lot of work, what we learn at Great Lakes and what happens in the real world, there are some differences. So I've tried to keep it more real. So in terms of the working hypothesis, so the first step we usually take is that even before we have seen the data, the first step is to have your own hypothesis. So in this case, the customers are moving. What could be some of the reasons that the customer is moving? It could be because of a compelling offer in terms of LTV or IRR. I'll explain what LTV and IRR means. Or it could be in terms of customer closed the loan because probably they got access to the gold assets or collaterals. They wanted their gold assets back. Let's say there is a marriage coming up, there is a festive season coming up, so they wanted their gold back, and hence they closed the loan and they got their gold back. Now, LTV and IRR are very two important concepts. Typically, they are very usually used in loans, business, and financial services. LTV is loan to value. So if my gold is worth 1 lakhs, how much of loan I am able to get by giving that 1 lakh worth of gold? Let's say if I'm able to get 75,000 out of the gold loan, then my LTV is 0.75 or 75%. And IRR is your internal rate of return. What IRR means is that if it's the rate. Usually, if any one of you have taken a loan, there is a rate at which you have to pay back. So it's the same rate of return. At what rate you will, at every month, what IRR or what rate of return you will be giving back the money on. And that's how some of these lending companies, they make money, because you're giving back them the loan after paying the interest amount. So you will first of all develop some of the working hypotheses based on your domain understanding, based on your business understanding, even before you have looked at the data. And then once you have some working hypothesis, then you will have the data and business understanding. So in this case, we had taken last 18 months data for closed loans. That was the sample that we have taken. Now, in real life, you will have a problem and you will not have a target variable. So even when you say attrition, it's a 0-1 sort of problem, but first you have to define what attrition means. So even in reality, whenever you will have a problem, you will have a data, you will not have a target variable, you have to create a target variable. So in this case, how we define attrition is that based on some of the trends that we saw, in the data that we captured, that we saw that customers who have iterated in the past 6 months, there are about out of all the customers who have iterated, 75% iterated within first 6 months. So we told that the 75% within first 6 months is the threshold that we need to capture. So in this case, the Y definition or the target definition is the customers who are iterating within first 6 months is the definition of my iteration. Then the next step is that you understand the nature of data, you do the data pulling, you prepare the data. It's quite a long exercise in itself. So you will see what are some of the variables which you have access to and which will be important in predicting the attrition. So in this case, some of the variables which were important, which we thought will be good for the hypothesis will be the location and proposition, so which state the customer belongs to, how much of IRR and LTV that customer has been given, what are some of the loan and asset details of the customers, how the demographics looks like, what are some of the bureau data of the variable. And when we say bureau data is usually captured if you have a past loan history from competitors. That's when you have a bureau history. And when you don't have if you have not taken any loan from the competitors in the past, you have no bureau history. That's how we usually generate a CIBIL score, based on your bureau history. And then you will also have your internal data. So internal data means what is the lending history of the customer, how much eligible amount you're eligible to take a loan, what is the interpurchase time between two loans, what is the interpurchase time of that loan. And then we did, so once you have understood the variables, once you have calculated, prepared the data, understood how the Y variable looks like and how the X variables looks like, then you will do the exploratory data analysis. Basically, you will do a univariate analysis where you will understand each of the independent variables, how their distribution looks like, what are some of the missing values, how the mean, median, mode looks like for each one of them, how the summary looks like, if there are some outliers. You will do for each of these variables you will do, and then you will do a bivariate analysis. So when we say a bivariate analysis, which means that with respect to your target variable, how each of these independent variables change. So for instance, with respect to state, with respect to value of goal, with respect to LTV, etc., how your iteration changes, and it helps you to derive a lot of meaningful insights. It helps you to tell the patterns in your data, which is very important because a lot of insights you will develop through the exploratory data analysis. So I've given two examples here. If you see for state Maharashtra and Karnataka, it comprises about 70 to 80% of your iteration, which means that these are the two states that you should be probably be targeting. And in terms of LTV percentage, if you see the inference, it clearly shows that people with lower LTV tends to iterate more versus people who have a higher LTV percent tends to iterate less, which is very natural, because if you're going to, let's say, give a very less loan to value to a person, then definitely that person is going to iterate more, versus if you give them 60 to 70% of their loan to value, then definitely the person is going to stay longer with you. So once we have done the exploratory data analysis, it's quite an extensive exercise. I've just given some snapshot of it, but it's quite an extensive exercise on its own. So once we have done that, then we had binned some of the continuous variables into categorical to make them categorical. We did some missing value treatment. There were some variables where the value were missing. So we clubbed some of the categories within the missing values depending on, again, business logic. There needs to be business logic. In the modeling exercise, we had used a shade algorithm because if you see, for each of these variables, you can have more than 2 split. So it's a good idea to use a shade algorithm because it has a multi-level split. It gives you an intuitive output. And it also helped us identify different customer segments along with their behavior and attributes. So the tree models were designed for 2 types of customers, because the behavior for a bureau hit customers versus a no bureau hit customer is going to be very different. The customer who has a past history with some of the other competitors who's taken loan in the past, his behavior, his level of information that we have will be very different from the one who doesn't have any bureau history. So that's why we made 2 models for 2 different types of customers. And it's a classification based problem where you say, 1, if the customer has eye-tried within first 6 months, and versus non-eye-tried where he has not eye-tried in the first 6 months. So I'll spend some time over understanding how to read this tree. So this 49.3% is for bureau hit. So typically in your data you have about 50% of bureau hit customers. And then the first important variable is state. If you see this 17 plus 17 plus, you can just refer to this thing. If you see, wherever you see the red marks, Maharashtra and Karnataka, they are generally the higher attrition. So within the 49.3, whatever X percent of 49.3% of the X population that you have, about 53% are eye-triting within Maharashtra and 55.4 within them eye-trite. So attrition is pretty high in these 2 states. And that's why we have captured for Maharashtra and Karnataka. For other states, it's not that high, it's pretty low. So this red and green tells you the attrition, and this percentage distribution on top of each one of these tells you the percentage distribution. So if you add up 47 plus 4 plus 4 plus 11 plus 17 plus 17, this gives you 100%. So 100% of the 49.3. So this gives you the distribution, the upper values, while these gives you the actual attrition in terms of percentage. So you see Maharashtra has the highest percentage of attrition. And then the next is the eligible amount, that how much a customer is eligible to get a loan. So either it can be less than 74K, 74 to 153K, and greater than 153K. So this is your next fitting criteria. Then the next fitting criteria is GL owners, whether you have a gold loan owners or not, less than 0 or greater than 0, where you don't have and you have at least 1. Then you break it with the affluent segment, less than equal to 3 or greater than 3. Typically less than equal to 3 is a lower, greater than 3 is your lowest affluent group, and less than equal to 3 is your high affluent group. And then LTV and IRR are again the 2 important levers. So how you read this customer segment 1 is that customer within Maharashtra, because we're just capturing from Maharashtra, with eligible amount less than 74K, has no GL owners, with affluence band less than 3, less than or equal to 3, LTV offered to them is less than 65 here, and greater than 65, and IRR, you can either give them less than equal to 21 or greater than 21. So these are some of the important variables when it comes to customer segment 1. And how it calculates Jade, as I told you previously, it's based on chi-square. It sees the p-value at each of these iterations, and it will see which category and which split is the most important split. Now, when you have created such, and this is something which the model will give you on its own. So you just have to know how to interpret the output. Now, once you have seen that, it gives you this output, it's no longer about, defining these customer segments, but it is more important that in terms of the AR impact, which is the account receivables, because at the end of the day, your model should have a business impact. And that's why you build a model. So how does if let's say I target customer segment 1, should I target customer segment 1 is my question, because there will be many segments like this. This is just one of the segments. Likewise, you will have many other segments which will have different definition. The eligible amount may change, the tier loan may change, the affluence may change. So likewise, you will have about 11 to 12 segments for just bureau hit customers. Likewise, you will have another 12 to 13 segments of customer segments for no bureau hit customers. So how do we define that which customer segments do we need to target? For that, we need to capture the AR impact. So how we have calculated this AR impact, it's quite there's a bit of calculations involved in it. I have not kept it purposely because it will tend to confuse you more. But the point I'm trying to make is that it's very important to be able to capture the business impact in terms of the monetary impact that your model is going to bring in. So if you see how we can say is that for this customer segment, if you offer a less than equal to 65 LTV, which is less than equal to 65 LTV, your attrition rate is 64%. While for the same customer segment, if you increase the LTV to greater than 65, the attrition reduces to 56%, which is 9% reduction, almost 8-9% reduction. And for that same customer segment, where if you're giving greater than 65, if you change the IRR from greater than 21 to less than 21, you are further reducing your attrition to 55%. So from 64, the attrition reduces to 55, which is 11% reduction. And this INR is what is your impact in terms of your account receivables. There is a calculation attached to it, which I have not kept here. But this is how you have to quantify in it to show, because just merely showing that your attrition is reducing from 64 to 55% is not going to really make your model a great one. You have to quantify it in some way or the other, and that depends on your business problem. So we see that the movement of lower LTV to higher LTV and lower IRR shows a positive impact on your account receivables. So once we have done this, and this is just one customer segment, there were like about 12 to 13 other customer segments for only bureau hit. There were other 12 to 13 customers for no bureau hit. Now we have to do a segment analysis for the chosen segments. Now how we have chosen the segments is, and this was with discussion with the business, that we chose the segments where there is a sizable population in terms of the number of accounts and customers. Because when you have to run a campaign, you need to have some sizable population to run your campaigns on. So if your customer segment, let's say if you've chosen one customer segment which has very, very minimal amount of customers, then it doesn't make a sense to actually target them. And then LTV and IRR were two most important levers that impact your attrition when controlled properly. And they were used as splitting criteria, because these are two most important levers. Either you can give a higher LTV or you reduce the IRR. These were some of the most important levers. Now, next thing which we also did is that we understood the customer behavior post the goal loan attrition. So the client also wanted to understand that, fine, the customer has attrited, they are no longer with us, but what do they do after they have iterated. And this usually you get from your bureau hit data, because in bureau hit data you have their past history. So we understood the patterns post attrition, and we understood that these repeat customers for gold loan, there were some other trade lines within the client organization also that they were looking for. They were typically your HL is your home loan, PL is your personal loan, TWS is your two-wheeler loan. And these are usually high ticket items when you compare it with a gold loan. So these were some of the things that they were iterating, and then they were looking to buy. Some of the other loan items they were looking to buy, both within the client organization and outside the client organization. Now, once you have understood that, as I told you previously, in previous slide, I told you that we took 18 months of data, right? Now, the similar scoring we did, because this whole modeling process took about 3 months or so. So we did a similar scoring exercise for the current active base. Because for the modeling we had used from Jan 15 to October 16, but we did a similar scoring to understand and basically stamp the probability on the current active base, because you will run the campaigns on your current active base and not on the customer base, which is already, let's say, I tried it, or probably they were there with you in the past. So you'll do a stamping on the current active base, and then once you have chosen the segments, then you have decided that what are some of the campaigns that we will be designing for these chosen segments. Now, there were three campaigns that were designed, and this was also in discussion with the business. So you see, a lot of business inputs are required, and hence modeling and creating model is just not limited to using a particular technique. There is a lot of business insights which goes into it. There is a lot of domain understanding which is required, and modeling is just one part of the whole exercise. So 3 campaigns were designed. One is the open line LTV. When I say open line LTV, means for these specific set of customers, we will increase the LTV, which is loan to value, which we are giving to them. So if, let's say, a customer is at 40% currently, we will, let's say, give them a 60 or 70%. Those are those type of customers who will respond better to open line LTV. Next is the IRR campaign, wherein we reduce the rate of return. So if, let's say, you're currently charging them 16% rate of interest, you will probably give them 2% less, let's say 14%. So these are the customers who will respond to the IRR campaign. And the third is the cross-sell campaign, because I earlier told you that some of these customers, they go and they buy other trade lines, a home loan or a personal loan. So there could be a cross-sell campaign, customers who will respond to it. And then once we have designed each of these 3 campaigns, the representatives will probably reach out to each of these customers, understand what can be done, and try to reduce the attrition. So I've given a snapshot for how we came up with the campaigns for each of these 3. The logic is different for each of these 3. I have just given for open line LTV. So if you see here, this is the segment which we have chosen. BH means bureau head, segment number 4. What is the sub-segment? They are currently having an LTV of less than equal to 65. Their eligible amount is greater than 55. Okay, so why we have chosen this is because their eligible amount is greater than 55,000, but currently we are giving them less than equal to 65. So it can be probably 30 or 40. So there is a huge margin that you can maybe upscale them. The number of accounts, currently we have 71. Now you have to see this thing, this particular thing. If you can see minimum opportunity amount per account. This is the most important thing. How we have calculated this 5,500 is, for this particular customer segment, I told you that the 55,000 is the minimum eligible amount. And currently, if you see, currently we are giving them less than equal to 65. So the maximum existing offered LTV can be 65. Okay, if you see this, the maximum existing LTV offered currently is 65, and the maximum proposed LTV is 75. So this is a thumb rule that you can't exceed beyond 75%. The maximum LTV that you can offer is 75 to any customer. That's a thumb rule in the industry. So 75% you can offer them maximum. So currently, if you see, this 35750 is nothing but your 55,000 into 65%. So this is the max. This is something which if let's say a customer is having an LTV of 65 at the moment, this is the this 35750 is the minimum that you is something that they have already, 35750. And if you give them, instead of 65%, if you give them an LTV of 75%, then your maximum proposed amount financed is 41250, which is your 75% of minimum eligible amount. So this 5500 is nothing but the difference of 41250 and 35750. So this is the minimum opportunity that you will, if you target this particular segment, and if you provide them from a 65% to a 75%, which is an open line LTV campaign, then the minimum opportunity per account in that particular segment will be 5500. And if you multiply this 5500 with the total number of accounts that we have in that segment, which is 71, you get this total minimum opportunity amount per band. Okay. And now if you see these four, now this is nothing but, so we'll have this, I've just showed two segments, there were about 12 or 13 segments. So for each of these segments, if you see, 5500 is the minimum. So likewise, what you can do is you will have 5500, and there is 749 for this segment. You will have for each of these segments, what is the minimum opportunity amount per account, right? So we'll just take quartiles. Now we just split these numbers into 4 quartiles, because you will have about 100, 200 such numbers. So we have taken the quartiles, so Q1, Q2, Q3, Q4. So if you see, Q1 is 729 to 4475, Q2 is 4475 to 5825, and these are 4 quartiles. And this is the number of accounts that you have, and this is the total opportunity. So if you see, it makes sense for us to capture these two segments, these two per account opportunity bands for running campaigns, because A, you have sizable number of accounts. You have about 370 odd accounts for which you can run these campaigns, and also the opportunity amount is pretty high. So that's how we designed a campaign for open line LTV. I mean, it may sound a bit confusing to you, but the point I'm trying to make is that, once you have built a model, it's a very important part of implementing the model, wherein you design the campaigns, and then there is a lot of logic which goes behind that. And of course, you have to quantify it with a business impact. I mean, that's how it works in the real world. Okay, so I have given that snapshot. Probably, I think we'll spend some next 10 minutes or so in terms of what has been my experience and what are some of the top learnings which I would want to share with you, and some of the different career fields which we can have in analytics. So some of the top learnings, and these are pure my learnings, so it may or may not apply to you, is what is that, and you would have seen the example which I have given to you, is that critical and structured thinking is more important than plain application of techniques or codes or tools. A lot of people focus on that if you will have to know everything like SAS or R or Python or etc. I don't think so. I think even if you know one of them in detail, and even if you have a good hands-on experience on one of the tools, and you know the techniques, few of the techniques, I think it's good. But of course, you can maybe upscale yourself as and when you require. But even more important than that, which will make you a good analyst, especially in this field, is how deeply or how structurally you can think. Because if you see through the example which I've given you, modeling is just one part of the exercise. There is a lot of structured thinking and critical thinking and asking the right questions which goes into it. So focus more on that as well. Of course, learning tools and techniques and being good in coding, etc., is also equally important. The second is that business and domain understanding is very, very important. I think people try to think that probably business or domain understanding doesn't make a difference, but it does make a difference to some extent. So certainly, like I'm in the financial services industry, so I need to constantly upskill myself in terms of the business understanding, because a lot of the inputs will be business generated, and a lot of times you will be selling your analytical solution to the business guys. So it's very important to have a good domain understanding, because if you don't have a good domain understanding, you may not be able to break the problem. You may not be able to understand what happens in the real world. So business and domain understanding is extremely critical. Then I think it's very important to understand the science and maths behind the machine learning techniques. So it's not about how good a code you can write. I think it's more important that do you understand the science behind, let's say we covered a lot of the concepts, Gini gain is there, then buy its way straight off is there. Do you really understand the maths behind them? Can you interpret the output? Because many a times your code will be redundant in nature. You've used a code in one particular project, you may be probably reusing in another project. So what's more important is contextualization. Can you really inference and make and can you really understand the output of it, and you can help it customize it as per your own problem. So focus more on that. It's not about the breadth of techniques, it's more about the granularity with which you understand these techniques. And I think the last thing is that you just keep things simple and connect the dots, because a modeling exercise is quite intensive, right from the data pulling to the actual implementation. There are a lot of dots attached to it. So as and when you work on it, try connecting the dots, try and see what leads to what. So that's very important. One is the data scientist, data analyst, which of course requires you to have a good depth of understanding in terms of tools and techniques. You need to have good coding skills, good structured thinking is definitely important. The other line of business is when you're working as a consultant or an engagement manager, a product or a delivery manager, you have a leadership role. That requires you to have a good breadth of understanding in terms of the tools and techniques, good structured thinking. Business understanding is extremely critical. You need to have good client and relationship management and project and delivery management skills. And then the third category is the sales or pre-sales or business development. I think this is something which will probably require a very, very broad level understanding of data analytics. You need not go in detail about how the statistics looks like or how the machine learning looks like. Even if you're well versed with some of these tools and techniques, it's good enough. You need to be well versed with the latest trends, and of course, relationship management is very, very critical, because you're the ones who want to get the business.
Decision tree is one of the most commonly used algorithms in the world outside, in the practical world. For some reasons, as you will see down the line, though it may not be one of the best algorithms under all situations. Under some situations, you will see that your logistic regression probably gives you better results than decision tree. But still, there is something about decision tree which makes it stand out. So let's see what does that do, something about decision tree. And before I go too far, there is no one single algorithm which is considered as the best algorithm. In production, we might use a mix of algorithms, put them together in one group. That group is called an ensemble, a French word, and we put that group as one single model. So don't be under any impression that this algorithm is better than that algorithm. There's no such reality. Some algorithms perform well in some situations. Other algorithms perform well in other situations. So we always use a group. Have you seen decision tree before? People who come with a lot of experience, management experience, decision tree is a very standard management tool that is used under certain specific conditions. What could be those situations where they use decision trees? In fact, decision trees used in our day-to-day life, we all use it every day. What should be our strategy? How should I, so that minimize my risk? Yeah, it is a kind of flowchart, if else. It helps you to take decisions in those situations where multiple states are possible and you don't know what's going to happen. You want to minimize your risk. So decision tree is one of the standard techniques that is employed to decide what action to take, what sequence of steps to take. People who have used decision tree, you'll find a lot of similarity between what I'm going to do and how it has been used already. Let me give you, for people who have not been exposed to decision tree, some brief idea about what this is. It can be used for classification as well as regression. The most of the time it is used for classification. Since you people have done a linear model, what was the data set on which you build a linear model? Was it MPG, miles per gallon data set? Cars, miles per gallon? What is the accuracy you got? 74%, 75, 76. That's the range in which you will get for that particular data set. Miles per gallon data set, the linear model will give you in the range of 74 to 76. Use decision tree on that. It'll give you 85+% accuracy. A phenomenal jump in terms of accuracy percentage, 85% plus, right? That is the beauty of this. So it can be used for classification, it can be used for regression, both, mostly used for classification. It consists of what we call the nodes and the branches, where the nodes represent some decision you're taking or some functions you're going to execute, some logical functions. Those functions will be executed on your independent attributes, the columns in your data frame. People who have not seen decision tree earlier before, this is the overall structure of decision tree. It can continue to any level. I'm just showing you some few levels. This is called the root node. All the things which are in what is the shape called? Oval. All these oval shapes are my nodes. Nodes represent any function call that you're going to make on your independent attributes. The result of the function can be this or this, binary result, true or false. So this is the result of the function executed here. These are the results of the function executed here. So at each node, we execute a function. All these are functions. This one is called the root node. And all those nodes which are not further divided, they are called leaf level nodes. LEAF, leaf. In between the leaf nodes and the root node, you have these function nodes. The algorithm that we are going to use, it is called CART, Classification and Regression Trees. CART, Classification and Regression Trees. It is a binary tree creator. It creates only 2 branches in every node. There are some commercially available algorithms which can create multiple branches at each node. You might be wondering why 2 branches? Why not 3 branches? There are commercial algorithms available, but the one which we use in scikit-learn, it is open source. It is called CART. Some of you might be wondering, that means it can be used only for binary classification. A decision tree can be used for character recognition in your English alphabet. How many characters are there in English alphabet? 26. You can use decision tree to classify those characters into 26 classes. So what will happen is it will do A versus others, B versus others, C versus, it will convert into binary. So it can be used for multi-class classification. It doesn't have to be binary class only. Just because the nature of the algorithm is to split it into 2 every time, does not mean it can be used only for binary classification. It can be used for multi-class classification. All right. What happens is at the leaf level, the nodes are of 3 types: root node, branch nodes, and the leaf nodes. The 3 types. At the branch nodes, we have the functions and then the result of the functions. Root node represents your entire data frame, data set. Suppose you're using decision tree for classification. You're going to classify things. For classification problem, whether a given record, whether a given image belongs to an airplane or a ship or a zebra, you want to classify a given image into one of these three categories. What decision tree will do is, it will tell you the probability. The probability that this is an aeroplane is 70%, probability that is a zebra is 2%, probability is something else is 30%, and it will give a percentage. Those percentages are given at this level, the leaf level. Those percentages are called posterior probabilities. By any chance, you covered probability-based analysis like naive-based? Not yet, right? So there we'll talk about something called posterior probability. When you do those analysis, you'll be talking about prior probabilities and posterior probabilities. Posterior means after knowing all these things, what is the probability that this belongs to a particular class? Hence the name posterior. I think it's voice operated.
Hello?
Yeah, there you go.
So the question is, what do we mean by leaf node belongs to the majority class?
So what happens is, suppose you have a data set. For simplicity's sake, let's take only two classes. Okay, you have a data set here. And these are independent attributes, I1, I2, I3, so on and so forth. And the target variable is a class. Okay. In the class, there can be two types. One is defaulter. Other one is non-defaulter. Defaulter, non-defaulter. You're working in a bank. The management in the bank has asked you to create a model where the model should take as input the parameters about the various customers, the income, the age category, where the person lives, so on and so forth. And the model should tell you what is the probability that this person will be a defaulter versus non-defaulter. All right, all of you with me? Okay. So the bank gives you all the historical data of people who have taken the loans. Some of them were defaulters, some of them were non-defaulters. When you create a decision tree, what happens is all this entire data set is used at your root node. There's a lot of detail to it. I'll come to those details gradually. And then, based on some function which is executed on one of these independent attributes, your data gets split into two. When the data gets split into two, here also you have some records, here also you have some records. Find out what is the majority here, defaulters or non-defaulters. Find out what is the majority here, defaulters or non-defaulters. Suppose the majority here is defaulters. Then this node gets the label of defaulters. Suppose the majority here is non-defaulters. This gets a label of non-defaulters, but please understand, it is not 100% non-defaulters. It is not 100% defaulters. It's a mix, but the majority is this. All right. Since it's still a mix, majority is this, I apply some other function on some other attribute on this data set and further split it. So this small data set gets further split into smaller set. And in this data set, suppose all of them are only defaulters. Then this node does not need to be split any further. It's already completely known. So I know that when somebody follows this path, he is likely to be defaulter. So I don't need to further split it. On the other hand, this one has still got some mix of defaulter, non-defaulters. Suppose the majority of them are non-defaulters. So on some other function which is executed on one of the other attributes, this data will be split again. And suppose the split is such that all these are non-defaulters, all these are defaulters, then you don't need to further split this. Now I know under what combination can a person become a defaulter. Maybe this combination of functions, this combination of functions. So at every node, it'll find out what is the majority class. The label of the majority class will be assigned to the node. But the fact is, unless you're at the leaf level, whenever you're in between the leaf and the root, the nodes will always be mixed. They will be contaminated. They will not be pure nodes. We want to reach a stage in our decision tree algorithm where we have pure nodes. Pure nodes means nodes which belong to complete defaulters only or non-defaulters only. When I reach that stage, then I know under what combination somebody becomes a defaulter, under what combination somebody becomes non-defaulter. So I know all those combinatorials, if I may say so, which lead somebody to become defaulter, and the other combinatorials which lead somebody to become non-defaulter. This is the pattern I'm looking for. This is the model I'm looking for. What we call linear models, which finds out the best fit surface for you, best fit line for you, which expresses the relationship between the independent variables and the target variable. The decision tree expresses the relationship between independent variables and the target class using these paths. The paths tell you how these independent variables are related to the target class. That is my model. And the beauty of decision tree is, well, not in scikit-learn, in the other language R, I can convert this whole decision tree into English rules. So I'll print out rules for me. If the person's income group is this, and his age is that, and his education qualification is this, very likely he's going to be non-defaulter. That English rules I convert into Java code and deploy it as my model. There's much more to it than what I've told you. I'll take you through the details, but to answer your question, that is what this means. All right. So if we are doing classification, then the objective of decision tree algorithm is to create as pure nodes as possible. Pure. Pure means the nodes should belong to only one class. That is the objective. In case you are using decision tree for regression, calculating the miles per gallon values, then the objective is at each node, the variance of the data points should be minimized. Now look at this. All of you know what is variance? What is variance? What is variance? Don't give me the formula. I'm not asking for formula. Understand the concepts. Variance is, on an average, how dissimilar two data points are. Variance means, on an average, how dissimilar a data point is from the central value. Xi minus x bar raised to power 2 divided by n. That is what we call variance. So you underroot it, it's called standard deviation. All these are nothing but a way of expressing how dissimilar a point is from the central value. All of you okay? The objective of the decision tree is collect all those records into the different cells such that the variance within a cell is minimized. All similar records come together in a leaf level. The variance within the cell is minimized. Right? It might sound slightly Greek or Latin to you right now. When you go further down the road and do some hands-on, bring up all these questions that are probably bothering you right now. This Gini index, this is called Entropy index. I'll show you pictorially the relationship between the two. What you see here in the red dots, these red dashes, this is the curve which represents the Gini. Gini ranges from 0 to 0.5. This is probability 0 to 1. Whereas entropy goes from 0 to 1. That is the only difference between these two curves. If I scale down the entropy curve, I scale it down, then this gray curve represents entropy scaled. And as you can see, between the two, there's not much difference. Between the red and the gray, there is not much difference. Gray represents entropy, red represents Gini. You can use any of the formulas, they give you the same result. The green one, we don't use in decision tree, so I'm not going to talk about this. This is more related to your confusion matrix. If you guys have done confusion matrix, have you done confusion matrix? Yes. It's related to that. Oh, you're going to say something. Oh, yeah, okay, good. Sure.
It touches 0.5, right?
0.5.
Does it mean that is the level at which we should be using Gini? Or if the impurity is more than that, we won't be able to use that Gini index formula there? Or
No.
What does it signify?
No. These are two ways of measuring your impurity.
Okay.
Entropy the impurity ranges from 0 to 1. Gini, when you use Gini formula for measuring the impurity, it ranges from 0 to 0.5. 0.5 is the maximum impurity in Gini.
Okay.
Right? So there are two different ways of measuring the same thing. One maximum is 0.5, the other is 1. And one more thing, it's important that I bring it out here itself. This relationship between probability and entropy going to 1 and going to 0.5, this will hold only when you have two classes, one versus others. When you have three classes, then this bar will go further up. This will go further up. Okay. I don't want to confuse you with that. So right now, let's keep it out of the picture. But keep this in mind. This relationship and the scale is true only for two classes. One versus other. A versus other, B versus others. Those kind of things. We call it OVR. OVR stands for one versus rest. You will see this when we run the algorithm, OVR strategies. These are the different decision tree algorithms available. C 3.0, it's also called ID3, iterative dichotomizer. Very old, we don't use it anymore. C 4.5, it came over with some limitations of ID3. Our cart is based on this. In Python, the cart algorithm is based on this. C 5.0 is the latest available commercial version, not open source, so we can't use it. In Python, we have implemented as cart, which is nothing but C 4.5. C 4.5 is open source algorithm. Advantages, disadvantages, all algorithms have advantages, disadvantages. The advantages of decision tree is simple. You don't need to know high-fi statistics. You don't need to worry about the p-values and all these things. Simple. It's very fast in your production environment. Classifying. Why is it very fast? Because the algorithm slashes your uncertainty by half in the very first level. So every level, it slashes the number of records you have to check by half, right? So its performance is very fast. It does well with noisy data and missing data. It does well with missing data. It treats missing data as another category. You don't need to process it. It does well with noisy data is something which I take with a pinch of salt, because this is what you will come across when you read in books and articles. But none of the algorithms can really handle noisy data, honestly. And as I told you, decision tree, even a slight change in the distribution of the underlying data set can change the tree structure completely. So I really you have to take this with slight pinch of salt, but this is true. It can handle numeric and categorical variables. You don't need to have very high-fi knowledge of statistics or mathematics to implement to make use of decision tree. The formula which I showed you is only conceptual. You don't even need to know that. Disadvantage, there are some disadvantages which we need to be aware of. As I said, it's biased towards those columns which are large number of cardinal values in them. Why? Because that gives the decision tree that much more room to experiment. This algorithm may not be very optimal in modeling relationships because this is an access parallel algorithm. Let me tell you what it means. Simple, nothing to worry. Are you all aware of the feature space? Have you heard of this word feature space? Feature space? Okay. Last session means the first half? First half. But you not heard of feature space before that? Nothing. Okay. All right. See, now you have a data frame with you. You have a data frame. And in this data frame, let's assume we have 3 independent variables and 1 target variable. I1, I2, I3. And all these are various values. Suppose the value here is 5. Suppose the value here is 7, 3. And the target value is some MPG, some 50. Then you have another variable here, 10, 2, 1. Then 15, 3, 6, something of this sort. And you have various values here, 20, 13, so on. This data frame, whenever you learn any machine learning algorithms, all machine learning algorithms are taught in the context of a virtual concept which is not real. That virtual concept is called a feature space or a mathematical space. Now, these 3 dimensions which you see here, this is your I1, maybe this is your I2, this is I3. The independent variables become the dimensions of this mathematical space. We call this data vector, okay? This is called a vector, data vector. Now look at this, 5, 7, 3. Maybe 5 on this, 7 on this, and 3 on this. Wherever these points meet, 3 on this, wherever this point, this data, this blue dot represents this record. Similarly, when I plot this 10 to 1, 10 on this, 2 on this, and 1 on this, wherever these points meet, this blue dot, it represents the second record. So every record in your mathematical space becomes a dot. Every record in your data frame becomes a point in the mathematical space. All right. So now let us assume, hey, you guys have done best fit model, linear best fit line model. Say yes or no. Yes. Okay. When was this? Last residency. All right. So you have this mathematical space. In this mathematical space, you have data points scattered over. Okay. And you said you did it for MPG, right? MPG versus weight of the car. Maybe you have the third dimension. Let's take it as one dimension right now. Otherwise, you have weight of the car, the acceleration, your horsepower, you have various other attributes. Let's imagine it's weight of the car. Okay. Now, this weight of the car has some distribution, and this MPG has some distribution. The best fit line that you found, the best fit line will always go between the X bar and the Y bar. Wherever these two meet, your best fit line will always go between these 2 points. The best fit model, the linear model which you came out with, will always go through the point where the X bars and the Y bars meet in the mathematical space. And that will be a hinge point. That will be a hinge point. Okay, that will be the hinge point. Okay. Why am I showing this to you? We are in decision tree. In decision tree, what happens is it's something slightly different. Linear model, it gives you a best fit line by reducing the sum of squared errors. Now look at what decision tree does. We are into classification right now, but we can do regression also. So first, let me explain classification to you. In this, imagine you have 2 classes, right? Imagine you have 2 classes where the classes are like this. You have been asked to build a decision tree based model which separates these 2 classes, the defaulters and the non-defaulters. So the first thing that you do is, suppose I take income. This is income. Your model says, if the income is less than some amount, the node which you get is most likely to be defaulters. Income greater than some amount, the node says likely to be non-defaulters. Though in reality is just the opposite. Right? In reality is just the opposite. So what your model saying is, if it tries to drop a perpendicular line, it tries to break your data into 2 sets by dropping a particular line at a particular threshold. It says anybody less than this is defaulter, anybody more than this is non-defaulter. Look at this. When you start with the original mathematical space, you have the root node. root node reflects the entire data set. Maximum entropy. This entire data set is then further broken into two, where you say income less than some amount, you come to this, or greater than some amount, you come to this. So it drops a perpendicular line here. Income less than this, defaulters, majority are defaulters, greater than this, majority are non-defaulters. So this node is non-defaulter, this is defaulters. But you're not happy because there's still some mix-up, heterogeneity. Then you look at age. You say that people who are a certain age, say for example, I take this age, anybody above this age is likely to be defaulter, anybody below this age is likely to be non-defaulter. So look at this node. This node gets based on age split into all these are defaulters, non-defaulters. This block which you see here, this is this block. This block that you get here, this is this block. As you can see, this block is perfectly homogeneous. It doesn't need to be split any further, but this block needs to be split. So I'll put some, I can't show you more than 3 dimensions, but I'll keep on putting boundaries which are parallel to the axis. That is why it is called axis parallel algorithm. It puts boundaries in a mathematical space to separate out the reds from the blues. And in the process, you keep getting these nodes. Each one of these nodes is a particular compartment in the mathematical space. But as you can see, when the distribution is angular, decision tree will find it difficult to separate the two. Whereas, if you had used linear classifier will simply put an angular line and get much better results than decision tree would. You'll need a very complex decision tree to get the same accuracy which a simple linear model will give you. That is a limitation of the second point here, may not be optimal as it is axis parallel modeling.
Say if the leaf node is going to have only one class.
Yeah.
So why should we need to do the predict prob here?
No, she wants in probability values.
It's fine, but if that leaf is going to have it's going to have only one class, what is the purpose of doing probability there? It's going to be 100%, right? Anyways, if it is a mixture of red and blue, then I can say that I can call it a probability.
Yeah. To answer this question, you just have to wait for 2 more slides where I will talk about this line. Large trees can become difficult to interpret, and I'll talk about this, elaborate this, and get your answer to that. We'll do that. Just hang on for a minute. His question is, if at the leaf level I have perfect homogeneity, why do I need probability? That is what your question is. It makes sense? Just hang on. No. Actually, it's a beautiful question. It's just come a bit early, so we'll take it up. So can I say that uncertainty is a function of heterogeneity? The more heterogeneity there is, the more uncertainty there is. Can I say that uncertainty is inverse of homogeneity? Homogeneity is also known as purity. Homogeneity is also known as purity. So when you're studying decision tree, you'll come across 2 words. One is called heterogeneity, which is also known as entropy. E-N-T-R-O-P-H-Y. You'll come across a word called entropy. Some people put a H, some people don't. And then you'll come across purity. P-U-R-I-T-Y. 2 words. Entropy and purity, they're opposite to each other. Let me play one more game. Okay, we'll not go too far into this. I give you 10 chances. You have to guess which famous personality I'm thinking about. You have 10 questions to ask. Okay, first question Sairam asked. What is the question? Male or female, gender. What did you ask? All right. So look at these two questions, Indian or other nation. I'm thinking of a personality, famous personality. The famous personality can be from anywhere across the globe, right? So if I say not Indian, then you're left with so many other personalities across the globe to look for. We don't know which one. He asked a question. The question was male or female. The moment I answered that question, half of your uncertainty is removed. Whereas the moment I asked that question, a part of uncertainty is removed. So in decision tree, what this algorithm does is it tries to ask that question, the first question, in such a way that it minimizes the drop in entropy is maximal. So the decision tree algorithm is built in such a way that at every level, it tries to ask a question just like you asked a question to me, resulting in a maximum drop in entropy. So let me give you detail about how this is done. We'll see that. Yeah. Good. Half of the entropy is gone. So this is an experiment which I was trying to do. You have a bag full of color balls. This bag is covered inside a cloth bag, and you're asked to pull out one of these balls. You don't know which ball is going to come out, and each ball, each color can take you to different situation. So you don't know what situation you're going to end up in. Maximum uncertainty. On the other hand, if I give you a bag like this, and I ask you to pull out the ball, you know what color it's going to come. There is no uncertainty. In short, heterogeneity means entropy. Homogeneity means zero entropy.
Broken up in a decision tree, and can we safely assume that the function is applied so that the entropy has gone down to the maximum extent possible when that function was applied at that node?
I'll answer that question in a while. Just hang on. Just hang on. Okay. All right. Now I will give you one fictitious example. Don't think too much about this example. It's a fictitious example. Data set is borrowed from the world of big data, where I used to work in big data. This is a sales data set. Okay. It has various columns in it. One of the columns is order priority, order number, location, and all these things. In this data set, there's one column called province. This province is the place from where the person has placed the order for you. You're working in maybe the retail giants. You're a data scientist working in one of these retail giants. And the task assigned to you is, can you build a model which, by looking at the various other attributes, will help me decide where is this customer located. So the last column is the location column. The screen size is limited, so I've shown you only a subset of the data set. Otherwise, this is a long data. So in the last column, you have values like some values here, Bisin Nagar, Adyar. Then you have other triplicates. You have other things over here in the last column. Okay. Now the objective is to find out, looking at the other attributes, can I guess where my customer is located? Okay. Since the target column is the last column, the target column is equivalent of the bag which I showed you on the previous slide. The fact that this target column has mix of various localities in the original data set, some records are from Adyar, some records are from Besanagar, so on and so forth, it represents the different color balls that you saw here. This is the situation you are in when you take the entire data set, and this is the target column. So this target column is the bag. Are you all okay? Are you all with me on this? What this decision tree algorithm cart will do is, it will find out for you amongst these independent columns, it'll select a particular column. And within the particular column, it will also select the breakpoint. When it breaks the data in that column at that breakpoint, it results in two smaller files. These two smaller files are your two nodes. The child nodes, each one of them is one single file. But in the process of doing this, what you have achieved is whatever entropy was there at this column, that entropy, when you look at these two columns, the sum of entropy of these two columns will be less than the entropy of this column in the original file. The entropy of the target column in the child nodes will be less than the entropy of the target column in the parent node. Then it's still, okay, this majority is some class, this majority is some class, but it's still a mix-up. It's not pure. You've still not got 100% purity. Then in that case, what it'll do is, it'll take this file, this node, and find out again one of these independent attributes based on which it will break that node into two smaller nodes. So this node is this node is this. Now what happens is, the entropy of the target column at this level will be less than the entropy of the target column at this level. The entropy of the target column at this level will be less than the entropy of the target column in this node. So the objective of decision tree is to break your data into smaller and smaller sets in such a way that the entropy of the target column in the child nodes is less than the entropy of the target column in the parent node. This is exactly what we do when we play guess the personality in 10 questions. This is exactly what we do.
Sample size like 30 or 40. Let's I'm just guessing it. Right? I think probably making a decision tree at a certain level is probably simpler or so. But when you come up with the actual data, the much larger population, right? So breaking that in terms of this entropy and decision. So what I'm saying, my question is more, have you seen predictive behavior on that, or something like when you do with a larger sample, like the decision tree totally changes somewhere else?
All right. He's asking a question which actually we are many light years away from answering, honestly. We need to actually get some more concepts in place. But to answer his question, decision tree, one of the limitations, weaknesses of decision tree is from the same universe, from the same population, you take two random samples. Create decision tree on one. Create decision tree on the other. The two are likely to be different from each other. Decision trees get easily impacted by the variance in the samples. Hence, when you're using this algorithm, it is very important to make sure that your sample is a true representation of the population, which is true for all the algorithms. But decision tree is more sensitive to those variances. Right? Man, that sounded like the perfect Greek. All of you know what is sample, what is universe, and all these things? Yes or no? Yes. Okay, what is the difference between the two? The sample and the universe? What is the difference? Psychoth? Population is constantly changing. I like that. Yes, you're right. Okay, all right. You're right. Sample is a subset of population, but very important point. You raised your hand. You want to say something? You. No? Okay. A very important point, please keep in mind. Population is dynamic. It's constantly changing. 2 weeks ago when I came, not 2 weeks ago, maybe a month ago when I came from airport to this place, there was no construction activity going on that road. And the route he took was totally different also. But today we got stuck in that mess on the way from airport to this place. Okay. So imagine you're working in Uber, you're a data scientist working in one of the taxi services, and you have been assigned with the task of creating a model where the model predicts the moment somebody sits in a taxi starting the ride, what time he's likely to reach his destination. That's what happens. When you sit in the taxi, even before the taxi starts moving, it tells you by what time you're likely to reach your destination. But in school, I was told that time taken is a function of distance by speed. This guy has not even started and it's telling me time. How does it happen? Welcome to the world of data science. What these data scientists have done is they have taken data from the past of whatever customer engagements and built this model for you. But this data which they have taken from the past, this is a sample. On this, you built a model. What about the data which is being generated at this moment when I'm testing the model? That is not part of this model. That is why we say universe or population is always dynamic. It's not only large, it's dynamic. It keeps changing. Whereas your sample is not only small, it's static. And this brings in a problem into data science. The problem is, the root cause of the problem is, your sample can never be true representation of the real world data. You might have a big data set up on cloud somewhere on AWS, terabytes of data, but still it's a sample because it's static. So that is a huge difference between the two. It's not just the size, it's also the fact that universe is dynamic, live, the data points keep continuously being generated, and new features, new attributes are coming into play, which is not reflected in a sample. That is why whichever algorithm you use, you have to make sure that your sample is as good a representation as possible. And one of the algorithms which is very sensitive to these differences between sample and the universe is this: preventing overfitting through regularization. There's a very important concept that you will have to be aware of when you're using decision trees. Decision trees are known as non-parametric algorithm. What do you mean by that? When you built a linear model, y equal to mx plus c, in that model, what are the parameters you have? M and c are the two parameters you have. Using the M and C, the algorithm gets for you the best fit line, which gives you the minimum sum of squared errors. Are you all okay? Alive? Yeah, great. Right? So it controls the M and C to find the best fit line for you. We don't have any such parameters in decision tree. We don't have any parameters which the decision tree algorithm learns from your data. Hence, it is called a non-parametric algorithm. So what happens is, when you make use of a decision tree, the decision tree will happily go and create a massive tree for you, which represents many of these cuts in the mathematical space, such that inside each compartment, you have only one record. Each compartment being one leaf. In each leaf, you have only one record. That's the question he's asking. But such trees, when you take into production, they fall on their face. They give you 0 error in training set, but in test set, their error will be very high. We call such trees overfit models. Have you heard of overfit, underfit, and all those things? Are you aware of these concepts? Fantastic. So the decision tree, when it has only one record at leaf level, perfectly homogeneous, 0 error in training set, but that tree is useless as a model because in the test data or in production, it will not survive. So what we do is, we roll back those leaves upwards. That is called post-pruning. We chop the trees and we roll back those leaves upwards. That concept is called regularization. You would have come across regularization in linear model also. If not, probably you will come across these later. That is called the lasso and the ridge regularization. L-A-S-S-O, lasso, and ridge, R-I-D-G-E. So when I apply the regularization on my trees, because I want to productionize it, then at leaf level, you will not find 100% homogeneity. There also you'll find mix-ups. So when you have mix-up, we can make use of probabilities. Hey, use a mic. You should stand here and then you'll know why we need that. Yeah, go ahead, shoot. Yeah. That's what will happen. So you go and visually analyze your tree. You will see that at leaf level nodes, you have one record in each leaf, 1, 2, and so on and so forth. That means you're in the overfit zone. And as a data scientist, I will never put an overfit model into production. I'll have to roll it back up. To roll it back up, I use what is called post-pruning. So when I do that, I'll end up with a tree with leaves which have mix-ups. They're not homogeneous.
One step above homogeneity is where you stop.
Maybe 1 step or 2 steps, I don't know.
Okay. That
depends on the situation.
Post-pruning situation.
In fact, that question brings me to another point which I'll discuss with you. Let me take these two, then I'll come to that. Yes. In fact, I was going to take the same question up. How do you know at what step you should chop the tree and not more? Okay. This is applicable to all the models, not just decision tree. How do you know how much should you regularize? Whenever you build your models, you always test your model both on the training set and the test data simultaneously. Beginners to data science, the mistake that they do is they try to build a model. I caught you again. I caught her again. Am I that boring? Much more. Okay, no problem. Hey, you want to grab a cup of coffee? I don't know whether it's allowed inside. It's not allowed? In Bangalore, it's allowed. Thank God. Okay. What was I talking? Yeah. Yes. Regularization. Whenever you apply regularization on any technique, you should know how much to apply and how much not. Okay. So whenever you build models, the beginners to data science, the mistake that they do is they try to build a model which gives 0 errors in your training set. That is a mistake that you should never do that. You should always allow the models to do errors in your training data itself. What your objective should be, minimal errors in the production, which is represented by the test data. Your test data represents the production data, which your model has not seen. Your objective should be to minimize the errors in the test data, in the production, not in training. Usually you'll find the accuracy that you get in your training environment, the controlled environment, is more than the accuracy that you get in production environment. You'll find that. It will often happen. 95% of the time, this is what will happen. Your model is giving you 95% accuracy in your controlled environment. When you take it to production, it becomes 90%. It will never happen the other way around, wherein your control environment is giving you 95%, in the production environment is giving you 98%. Very unlikely. What should not happen is, in your controlled environment, 95%, in the production environment, 80%. That should not happen. That sudden drop in performance indicates that you're in overfit zone. So what we do is, when we build the models, we test the models both on this is my complexity of the models. Complexity is also a function of number of dimensions or attributes. It also includes whether your model is a simple linear model, quadratic, cubic, those kind of things. I check, this is my error. I check my training error and my test error both. Okay, I keep building my model. I run it on training data. This is training. And I also run it on test data. You'll often find that as you increase the complexity of a model, your errors come down. But after some point, the test error starts going up. Your training error comes to 0. After some point, your test error starts going up, your training error starts going towards 0. That point, this is called overfit zone. This is called underfit. Right fit is somewhere in this. So when I build a decision tree, a non-parametric algorithm, it creates a very complex tree for you. You'll see this when we do the hands-on. I will show you that that particular tree on training set, it gives you 0 errors. But on test set, the errors jump significantly. You are in overfit zone. What should happen is that model, whichever model you build, should give you more or less similar accuracies in both your training and in your test. Such models are likely to generalize in the production. All of you okay? So decision tree, we will have to prevent overfitting. We will have to do it. Whenever you're reducing decision tree, you have to do regularization. It does not assume any kind of linear relationships between independent and target variables. It is non-parameterized algorithm. It does not have any parameters to find the best fit surface for you. If left untouched, the decision tree will create a very complex, uncontrolled model for you, which will be overfit. To avoid overfitting, we will have to use regularization. I'll show you how to use that. And for that, we will use certain parameters Those parameters are called hyperparameters. In modeling, there are two types of parameters. One is M and C. These parameters are called model parameters, which are learned from your data set. There are other set of parameters which are called hyperparameters. They are used to control the behavior of the algorithm. Long time ago. I can make out. Where are you stuck? No. Hey, Ram. Not only Ram, anybody. If you have any problem, don't hesitate to ask. Don't get left behind just because you think it's not right to ask. Don't feel that way at all. Where are you stuck, Ram? I'll come to you. Just hold. All right, just hold on. How about your neighbor? Where's your nameplate, sir? The chair is blocking it. Shiva. Yeah. You're also stuck somewhere? You're with me? 100%. Yeah. Ram, then you can bank on him. Right? Good. But Ram, feel free to ask. Don't hesitate. You had a question. Regularization. What do you want me to repeat on regularization? Okay, no problem. Yeah, sure. Let's do it let's start from here then. We have to plot error versus complexity of model. We should always do this. For the time being, you imagine complexity is equal to the number of dimensions, attributes you use in your model. Complexity can also be y equal to mx plus c versus y equal to m1 x1 plus m2 x2 square plus c. That is also another way of bringing in complexity. So I'm looking at the first one, where you keep on adding more and more dimensions to your model. That way you bring in complexity. Okay? Whenever you build your models, you will never get the best model in the first iteration. At least this has never happened to me. You'll always get your models in multiple iterations. The best model which will survive in the production world and give you the results, you'll find that model only after iterations. So in first iteration, I might take MPG versus weight, acceleration, and something else. In the second iteration, I might drop acceleration and take weight versus horsepower. In the third iteration, I might say, okay, horsepower and weight, they are linearly related to each other. Let me combine them into one and use that one dimension for my MPG. So I might iterate through all these things before I finally settle down for a model which gives me good results. All these iterations that you do is what is shown here, moving from simplest model to complex models. Every iteration, I do a test against both the training data and test data. Let me show the test one in the red. Okay. So this is my test. I'm deliberately showing tests slightly higher than training because usually when you break our data into 70-30, you broke your data into 70-30? You gave more data for learning, less data for testing? 80 for training, 20 for testing? Yeah? Obviously, it makes sense. Okay. You give more data for the algorithm to learn from and less data for the algorithm to test on. There is a very basic assumption you're making here. I'm not sure whether you're aware of this. When you prepare for your board exams, the reason I'm giving that example is my daughter recently took the board exams. The more the training set she has, more sample questions she has, more likely she is going to perform well in the board exam. Right? So in the board exam, she is going to get only a few questions, 20 questions, but should have prepared herself from thousands of questions. So we assume that the 20 question patterns will be somewhere here in this 1,000 question patterns. Are you all with me? So if she has done this 1,000 well, this 20% questions would be a subset of this 1,000. The patterns would be a subset of this. That is what our assumption is. But in data science, this assumption is always many times violated. When I break my data into 70-30 or 80-20, some part of the 20, the patterns in the 20 is not there in this 80, is not there in the 70. Those patterns your algorithm doesn't know. Right? Now you're going to check this model onto this test data. In the test data, there are some patterns which this model has not seen before. So it starts giving you higher errors in your test sets. But what you will see is, as you increase the complexity of the model, you will see that both the training error and the test error, they keep falling down. They decrease. But what you will notice is, after some point, your training error keeps going down, your test error goes back up. This point where the training error starts deviating upwards, this is my best fit point. This side, I'm in overfit zone. My model will give me 0 errors in training. My daughter will give me 100% score in all her sample questions. But in production, in her board exam, she'll bomb. Right? Fortunately, that didn't happen. So she's in overfit zone. Same way, underfit is also not good. Underfit is suboptimal model. Overfit is useless model. You have to be somewhere in between, the right fit model. You're experiencing the same patterns, same 20 questions now. Same patterns, that's what we do. Yes, sir, very good. Yeah, there is a concept. Absolutely, there is a concept. That's what I'm telling you. That happens when, okay, there is a concept behind this. Okay, let me finish this off. What time is the tea break? Is it 3:30 because it is 3:30 now, or is it 3:30? It's 3:30? Anyway, Piyush will come and knock the door, so I guess, okay, that's okay. Coming to your question, Saikat, there is a theory behind this. There's a concept behind this. What happens is, when you're in the overfit zone, your model is flexible, it's trying to adjust to all the distribution of the data points in the mathematical space of the training set. Let me explain this to you. So this is my mathematical space. This is my independent attribute I1. This is my independent attribute I2. And my data points are distributed like this. There are 2 classes, and the data points are distributed like this, somewhere like this. I want to separate these 2 classes. Okay. You build a model, a simple decision tree with only two attributes. It's not a good decision tree, will not give you good results. So I make use of a non-linear model, and I draw a very complex surface like this, which cleanly separates the blues from the reds. Believe it or not, this surface can be represented in mathematics as an equation. You must have heard about Fourier analysis if you guys come from that background. Fourier analysis can build a very complex function for you, and the model will give 0 error in testing and in your training. When I take this model onto another mathematical space, the test data, in the test data, these blue points and the red points might be distributed in different ways. They might be different in positions. They might be in different positions. It's not guaranteed that it will be the same positions. Now, when I take this model as it is and transform it here, assuming it goes something like this, your model is going to give too many errors. Can I take the liberty of showing you something? We'll be slightly deviating here so that you get the concepts in place. It is connected to the regularization concept, which I'm going to talk about in decision tree. This is 2-dimension, and this is the nature of your universe, your population. Data points are being continuously generated around the central values, and your data points keep on increasing in volume. Okay. What also happens in the universe is new attributes come into play, which are not shown here. So your population is always dynamic. It's not only large, it is dynamic. Out of this population, I take a snapshot. That snapshot is called my training set. Snapshot is static. It doesn't change, and it's smaller in size. In this snapshot, I create a very complex model to separate the greens from the reds. 0 error in training. I take another snapshot of this, and that snapshot, the data points might lie somewhere else because they are jiggling when you're capturing them. They might lie somewhere else with respect to their central values. When I bring this model and project it onto this, it starts doing errors which it was not doing earlier. So you're in an overfit zone when your model is extremely complex and gives you very good results in your training set, But when you take that model to the test data, the model's performance drops. That happens because you absorbed the patterns in all the distribution patterns, the random noise in this data set you absorbed into your model. But that model, when you put into this, the noise is different. Noise is the jiggle. How far away the data points are from the central values. It's different, so the model performs poorly. There's no exact point. This is the only way, I told you, right? The point where they deviate. That is likely to be probably the best fit. Probably. Use a mic. Where is the mic? Please pass it on to him. Please pass it. We'll discuss this point, and then I'll take one more slide. Hopefully the console will fall in place, then we'll move on. Yeah, go ahead, shoot. Make it.
Point.
Best fit line.
Yeah. But you continue to use the model in production, your noise will continue to increase after a period, right? Which means your best fit line will keep changing.
Okay. What he's saying is, let me correct me if wrong. It's actually a very important point. A model is not for life. Every model will need to be recalibrated. How frequently you recalibrate the models to get the same accuracy level depends on your domain. Now, I took the example of time taken to travel from A to B is a function of I built a model. But that model which I built 3 months ago will not work in today's environment because the reality has changed. The reality in the outside world has changed. There are so much of construction activities going on, so the time it's going to take from traveling from airport to this place is going to change. So all models in the real world, they will drop in accuracy over time because the population keeps changing. What you're saying is right. Yeah, there is. You can actually track the drop in performance of your models over time, and below a certain threshold, if you people have come from the quality world, we use something called control charts. The control charts have upper control limit and lower control limit. So the moment I see some trends within the control chart or going above them, then something is going wrong. Your model is a process. A process behavior has to be mapped. No. I am not aware of any formula where you can fix up the frequency. No, it's not there. To my knowledge, it's not there. You'll have to keep a track on this. There has to be a feedback loop. There has to be a feedback loop. Feedback loop may be automatic or through a manual process, but it has to be. Yeah, a lot of people will do that. They automatically capture your data from you. They do that. There has to be a feedback loop, otherwise you can't do it. I hope really it will bring in the problem clearly to you. This is my iris data set. All of you know iris data set. It is about the plants. In that, there are 3 types of plants. I don't know the names, but blue, red, and yellow. This is the distribution of the plants on one particular attribute. The sepal width, one particular attribute. This is how the data is distributed for the 3 different classes. This is the entire data set. Out of this data set, I take a random sample. I break that sample into train set, test set, 70, 30, 80, 20, whatever. Look at the difference in distributions. Look at the yellow. The moment you take a sample, you change the distributions. Even if you use random functions. The moment you change the distributions, you change the central values, the mean and the medians. The moment you change the mean and the medians, the model, the linear model which you're building, which goes through the mean and the median with central values, the model will change. If you have built a model on this, the model would have been different than what you found on this. That is why when you take this model and put into production, the model will perform more errors. Now look at this carefully. So when I took a sample from this, the distribution changed, and look at the difference in distribution of the train set and test set. When the distribution is so different between the train set and test set itself, how do you expect a model which is performing well here to perform well here? Look at the second line. Another random function on this and second set of samples. Look at the difference in distributions. The data is same, but I took 2 samples using random functions. The distributions changed. So whenever you do sampling, you're introducing bias errors. You can't escape it. So when you break that data into training set, test set, you introduce more bias errors. That is why a model which performs well in training is unlikely to perform equally well in testing or in production. And decision tree, it is non-parametric. We have no parameters to control and find the best fit. So it'll create a complete complex model in your training set. So in training set, decision tree will give 0 error. That tree, when I take it to this, the distribution is completely different. So the tree will perform poorly. This is a particular characteristic of this particular algorithm, where it can easily become overfit. So we will use regularization techniques to prevent it from becoming overfit. The question that he asked was, if I got him right, the question that he asked was, should the entropy at this plus this be less than this? That's what he asked. That's what he asked? Yes, the answer is, the entropy at the child level should be less than the entropy at the parent level. I'm not saying entropy of this should be less than this should be less than this. I'm not saying that. I'm saying the total entropy at this level should be less than entropy at the parent level. Child level, parent level. Okay? All right, let's move on. Now, this might look like slightly dangerous stuff, but believe me, it's very simple. Right? Don't worry about this. You understand the concept. It's important. Formulas are all there in the libraries. We just need to download the library and use it. But it doesn't hurt to see the formula and the concept behind it. So don't worry about the formula. Let me explain this to you. There is a history behind this. The history is, there was a person called Shannon, Claude Shannon. Heard of his name? Claude Shannon? Claude Shannon? Who says yeah? Anybody who's heard his name? Exactly, Molly. Yeah, you're right. Hey guys, he is one of those guys because of whom we are earning our bread and butter today. He was a father of comp science, Claude Shannon, information theorist. And he did a very fantastic job in this area. So I think it'll be good if you just go and explore on Google who this guy is, what did he do. What he said is, Claude Shannon said is, he made a graph where this represents this relationship between probability and entropy. Entropy shown by the symbol H. He had a physicist friend who was expert in thermodynamics, and we come across entropy in thermodynamics, and this guy unfortunately asked him for a name for this concept, and that guy said entropy. Otherwise, there was no reason for it to be called entropy. Okay, he wanted it to make it look something great. Okay, it is great, but it's called entropy. What happens is, when you're in a situation where multiple outcomes are equally probable, we had blue and red. When you put your hand into that bag and pull it out, the probability of getting red was 2 by 4, 1 by 2. Probability of getting blue was 2 by 4, 1 by 2. You are in a situation of maximum uncertainty. You didn't know what's going to happen. Uncertainty is measured on a scale of 0 to 1. So when you are in a situation where you have to take a decision and it can lead you to multiple states with same probability, you're in a state of maximum uncertainty. So probability is 0.5, maximum uncertainty. Are you all with me? When we took that bag where two of the pen caps were blue and the two of them were red, the probability of getting red and blue was 0.5. At this situation, you had maximum uncertainty, 1.0. I replace all the red with blues. 0 uncertainty. So when you know the probability of something happening is 1, the probability of this, suppose this is probability of picking up blue from the bag. When you know the probability of something happening is 1, there is 0 uncertainty. So you're at this point. Are you all okay with me? Lady at the back, what's your name? Yeah, you. Tamil Selvi. Yeah, got it right.
the probability is, we are not caring about the probability. We are coming to a conclusion that this is a defaulter and this is not a defaulter. But all the learning models is about predicting something. So in that case, how do we say this is a model where we can say the probability? It is like confirming that this belongs to this group.
No.
So
yeah. See, all these good question. Did you get what she's asking? Though I was expecting something else. What she's asking is the decision tree at the leaf level, if it's going to classify something as default or non-defaulter, right? And you're talking about probabilities. All these classification algorithms, whether you use decision tree or logistic or naive Bayes, anything, all of them have a function. That function is called proba. Predict dot proba. Proba stands for probability. You don't want classes, you want probabilities, it will give you probabilities. So decision tree can give you probability values. Right? Does that answer your question? Okay. All right, shall we move on? Yes.
I just get a feeling that it is looking like the probability prediction of a logistic regression.
Boss, all these are same concepts coming in different bottles.
Okay.
I'm glad that you noticed that. All these algorithms do the same thing in your feature space, in your mathematical space, but they do it in different ways. Right? So it's a very interesting thing when we, unfortunately, you people have not covered. Once you cover all these algorithms down the line, then hopefully one day we'll meet where I'll show you how these different algorithms do the same thing, but in different ways. So you got it right. Shall we move on? Any questions? No? All right. You understood these 2 points? What Claude Shannon found out is in mathematics there is a function. That function is called log to the base 2 of pi. This function takes a beautiful shape like this. Log to the base 2 of pi, when pi is 1, log to the base 2 of pi is 0. Actually, it has a negative term. I'll talk about that later. So when log to the base 2, you can do it on Google if you wish. This is equal to 0. Log to the base 2 of 0.5 is 1. So he found out one function in mathematics. He knew it. It gives you this relationship between the probability and the entropy. However, there's one small problem. The problem is log to the base 2 of anything less than 0.5. It tends to go towards infinity. It goes towards infinity. We want it to come down towards 0. We want it to come down to 0. Yeah, it is a minus. I've removed the minus term right now, but it is a minus. So I want this curve to come down. To make it come down, I multiply it with by pi. So probability of getting blue, when it is 1, this becomes 1, this is 0, 0 and 1 is 0, so on and so forth. When probability of getting blue is very small, this small term will pull this whole thing down. This term is going towards infinity here, but this pi will pull it down towards 0. Hence, this equation which you see here, entropy is a function of pi log to the base 2 of pi. This expression reflects the relationship between entropy and probability. Don't worry about the formula at all. Just keep in mind how the probability of something happening or not happening is related to entropy. That is uncertainty. That's all you need to know. Okay, formula and all is not required, but this is what happens under the hood.
This brings us to the end of this video on classification with decision trees. Thank you very much and have a great learning ahead.
I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.